Hey everyone, this is Mariana and this is my project, Ocean Response on the Maritime Continent to the Madden-Julian Oscillation. Located in the warmest ocean area in the world, the maritime continent, or MC, affects the climate in many timescales. I particularly focus on the intraseasonal variability in the ocean there, which is associated to the wind during the Madden-Julian Oscillation. However, the importance of the intraseasonal remote wind and the wind over the MC have not yet been investigated. That is why this project will determine the average effect of the MGO on the currents of the MC. With the composite and spatial regression, we'll try to determine what percentage of the MC currents variability is due to local and to remote wind. The study site included the maritime continent and the eastern side of the Indian Ocean, and the study employed high-com reanalysis data of 0.08 degrees resolution, the daily mean values of current and sea surface height for 2003, 2015 were used, and for the second part, the daily winds at 10-meter height obtained from MCEP's CFS reanalysis were used. Regarding the methodology for the first part, using the information from an MGO index, the datasets were subset to let only the days that correspond to the 8 MGO phases. Then the temporal mean was calculated, obtaining the average behavior per phase. Lastly, the velocity components were converted into a vector field, obtaining the final sets that are used to visualize the composite. For the second part, as ArcGIS linear regression doesn't take multidimensional data as input, this method was performed considering data from one particular day. To start, the data was transformed into integer format and then to polygons raster, and after that, 3 experiments were performed. On the first one, the wind data was united to the current data to form one input layer. On the second one, the wind data was clipped into 2, remote and local. And on the third, this was repeated using remote wind lagged 5 days. To consider the time it takes for the effect of the wind to show in the current. And in all cases, the generalized linear regression was performed and the resulting model performance parameters were compared. Here we have the result of the MGO composite of the current in the MC. We first see eastward current anomalies along the equator associated with positive SSH anomalies that propagate eastward and then along shore, and these are followed by negative SSH anomalies with westward currents also propagating eastward, and these results are consistent with the coastal Kelvin waves mostly generated by MGO winds. So here are the results for the second parts of the linear regression. For the first experiment, the R-square value, which measures the goodness of the fit, is very low. This was expected as the wind is definitely not the only forcing of the currents, but it's still very low. For the second experiment, the R-square and the adjusted R-square values are better than the previous one. The ArcGIS information criteria can be used to compare models, with the lower values indicating the better ones. Here the AIC is lower, which also indicates the model is better. And finally, even when the results for the third try using the lagged wind seem to be better, they are all still very poor. So to conclude, a composite of the MGO currents was calculated and it showed the expected coastal Kelvin waves generated by the MGO winds. This process was pretty straightforward and it would be easy to reproduce in the future. For the second part, as ArcGIS's generalized linear regression tool doesn't run with temporal data, the experiments had to be performed using only a specific date of data, and the linear regression gave, in all cases, very low R-square values, which probably means that more predictors are needed. In spite of that, it showed best results when considering remote wind lagged 5 days, which was in some way expected. Thank you.